So welcome back to the last lecture before spring break, which I'm sure we're all looking forward to. I have 2 and possibly 3 goals today. One is to finish this lecture, which I have one topic left on, which is multigrid, which is the ultimate fastest algorithm for this problem. That'll take most of the time. Then I have a few slides, 15 or so, with class project suggestions, because a number of you had asked for ideas about both how to organize class projects and write a proposal, and then particular ideas of what to do. Now, many of you have your own, application that you brought with you that you want to parallelize. That's great. I have lots and lots of other suggestions. Some of them are just examples from previous classes, which might, inspire you to do something similar or more advanced than what was done before. And then people have also just sent me emails saying, I'd like somebody to work on this. Can you find a student to do it? Anyway, I'll just tell you about some of those too. There's a lot of interest. So let me now continue with this. Oh, and then if there's any time left over, there's one even older topic that I didn't do in lecture 12 on dense linear algebra, which is the lower bound on how little you have to communicate. And that's a few slides, and if there's any time left, I would cover that topic too. But let me now go down here to lecture 31, slide 31, excuse me. And start here. And so in case we needed any reminder, that's the system of linear equations we want to solve in 2 dimensions, 2D Poisson. You just take an average with your nearest neighbors. And in 3 dimensions, it would have a 3-dimensional stencil, and you average with your 6 nearest neighbors plus yourself. So here is the list of all the different algorithms that we have discussed so far, and a few that we haven't yet, to solve this problem, sorted in order from the sort of slowest algorithm, but the most general, that pays no attention whatsoever to the fact that we're solving Poisson's equation, works for anything, dense Gaussian elimination, takes n cubed. And then these are, in some sense, sorted in order of how much structure of this particular problem, Poisson, they take advantage of, and therefore they keep going faster and faster until you get down to the bottom one on the list, which is the topic for today, which is multigrid, which takes only order n operations to solve an n by n system. Of course, just writing down the answer takes order n, so we're never going to do better than that, which is why I call it optimal. So these columns here, just to remind you, we've seen this picture before. This is just how many flops you do. So, on a sequential machine. If you're on a magical parallel machine with as many processors as you like and communication is free, that's called a PRAM model. This is how long it takes. This is just a measure of how much inherent parallelism there is, and the answer is there's a lot. This is how many processors it takes to do that on this magical parallel machine. Of course, we're not going to have that many processors in general, and this is how much memory it takes. So as I said, this is today's topic, which is the fastest algorithm. I'm going to tell you about it in this context of structured grids. That's the simplest way to understand it, and indeed it's a very common solution technique. And then at the end I'll have some slides about how it generalizes to unstructured grids, because people certainly do want to use it in that case. And so just to remind you of the motivation for why I'm going to do this different kind of algorithm and why the other ones weren't good enough, is that all the algorithms I've talked about so far, Jacobi, SOR, successive over relaxation, and conjugate gradient, or anything that basically all it does, it takes your matrix and it multiplies vectors by it. That's all those guys do, is that they can only move information 1 grid cell at a time. And that's because if you look at the pattern in the matrix, I'll have a picture on the next slide, everybody only depends on their nearest neighbors. And so if you keep doing matrix vector multiplies, data moves 1 grid cell at a time. And so how long does it take to get across an n by n grid? It takes order n steps. And since that gives us a lower bound, we're going to have to take at least order n steps in order to converge. SOR actually works that way. It will get you to hit that lower bound. But we want to do better. We want to converge in this iterative scheme in order 1 step, a constant number of steps. And for that to work, we have to move data a lot farther than 1 grid cell, 1 neighboring grid cell at a time. So here's just the picture I've shown before, which illustrates that point. Suppose I want to solve 2D Poisson. My right-hand side is non-zero in the middle only. Here's the true solution. It's what you expect. It's a 1 over r kind of potential function. So it's non-zero everywhere. Now, if I take 5 steps of Jacobi, what do? I take every mesh point here, and I average it with its nearest neighbors, which are all zeros out here. And so they stay 0, except for the immediate neighbors. And after 5 steps, this is what I get. And it's dead flat out there. And so there's no way I can do better than have the perfect answer within 5 steps and dead flat 0 outside of it. And so the error is going to be at least the size of that cliff from the true solution down to 0, 1 grid cell away. And that's going to keep me from converging very fast unless I send information much farther than 1 grid cell at a time. So this is the 3rd time we've seen this big idea. So let me just advertise it again. It's come up in graph partitioning. It's come up in fast multipole. And it's coming up here again. And the idea is that when something is far away, in some physical sense or even in some graph theoretic sense, it gets simpler, or we'll just make it look simpler. And if it's simple, you don't have to send very much information to tell you all you need to know about that stuff that's happening far away. And so when we did that with graph partitioning, how did we do that? We just took every other grid point in the graph, and we said, well, that's a good enough approximation. We'll just take half as big a graph. And then things far away get half as big. The fast multipole method, again, we approximated distant galaxies by their mass, center of mass, and their total mass. And that was a perfectly good approximation. And we're going to do the same thing again for multigrid. And now the way we're going to do the approximation is actually similar in spirit to what we did with graph partitioning. We're going to take our very, very fine mesh with n points in every direction. And we'll just take every other mesh point. So we'll have n over 2 points in every dimension. And then we'll be able to move points twice as far by going to nearest neighbors in that coarser mesh. That's still a pretty big mesh with n over 2 points. How will we solve that problem? Well, we'll take half again as many points in every direction. We'll get n over 4. It's the same recursive trick that we used in every one of these other examples. So there's a saying that any trick used 3 times is a standard technique. So now we can consider this a standard technique. So here is kind of a picture of what I mean by approximating something that's, this is the true answer that lives on this fine grid. I want to approximate it by something that lives on a coarse grid where I've taken every other mesh point. And it's pretty clear from this nice picture that I've chosen. This is a nice smooth surface. And if I just take every other mesh point, it's still a nice smooth surface, and it's not a bad approximation. That's the kind of thing I'm hoping for. The trouble is we have to figure out how to deal with things that look like that, because that could perfectly well be the solution too. And if I take every other mesh point, something bad is going to happen. So I have to figure out how to deal with that. So here's the algorithm. As I said, it's going to be recursive. I'm going to replace my problem, which is what I want to solve on this fine grid here, by solving this problem with half as many points in every direction, so a quarter of as many points total. And I'm going to use this solution as a starting guess to this one. So I'll solve this problem, get that answer, use that as a starting guess to this one, and you got to admit it's pretty close. And then I'll improve it a little bit. It won't take much work to get this approximation to look like that. Now, this is still a pretty big problem. I've only thrown away 3/4 of the mesh points. How do I solve it? Same idea. I do it recursively. I take this guy, call him the fine mesh, take every other mesh point, and just keep repeating that, and it will work under certain circumstances. Okay? So to write down the algorithm a little carefully, I have to introduce some notation. So let me just write it down in 1 dimension. This algorithm isn't worth it in 1 dimension, but then I'll write it down in 2 dimensions. So to make everything work out nicely, I'm going to assume that the number of mesh points is a power of 2 plus 1, so I can take every other one every time. And here's some examples. I'm going to go from 9 mesh points down to 5 mesh points down to 3 mesh points. And I'm going to let P superscript I be the problem of solving my Poisson equation, my 1D Poisson equation, on this problem with 2 to the I plus 1 mesh points. And that's going to be a linear system. And there it is. There's Laplacian, whose dimension is 2 to the I plus 1. There's the solution, and there's the right-hand side. And here's going to be my sequence of problems. There's going to be my finest problem on this very dense 9-point mesh. And then here's going to be my next problem on my 5-point mesh. And here I'm just going to be on the 3-point mesh. And so my notation is going to be that the only unknowns are the guys in the middle. I'm going to leave off the guy at the end, because those are the boundary conditions. Those are going to be fixed values, like I'm tying the string down at the ends. And so when I talk about my mesh, there really is always take your neighbor to your left, to your right, and average it with yourself. Just, it's notationally simpler. So the unknowns are going to be 2 to the m minus 1 guys in the middle, but the total mesh is going to be the 2 to the m plus 1, everybody in here. So the nodes labeled 2 are the every other mesh point. That gives me the coarser problem. The nodes labeled 1 are the ones that give me this finer problem. But the only, here I have one unknown. So when I finally get down to that, I can solve it. One equation and one unknown I can do. And then I move back up there. I have 3 equations and 3 unknowns. And there I have 7 equations and 7 unknowns. So that's the 1D problem. And I'm just going to use the exact same notation for the 2-dimensional problem, which is more interesting. Now it's worth running the algorithm. So I'm going to have a mesh again, 2 to the m plus 1 by 2 to the m plus 1. The ones on the boundaries are known. They're fixed. The unknowns are just the guys in the middle. So this smaller square of size 2 to the m minus 1 by 2 to the m minus 1. And here's the finest problem, P3. There's the next coarser problem, P2. And there's the coarsest problem of all. The only unknown is the guy in the middle, the 1 by 1, and that's P1. OK, so those are the statements of all the problems. And each of these, I'm going to solve Poisson's equation of different dimensions. OK, so now, in order to do that, I need a little more notation still. Sorry. So here, this is just repeating what I said before. I have these problems at various coarsening levels. So I'm going to have P sub I as the problem on the grid of size 2 to the I plus 1 by 2 to the I plus 1. BI is going to be the right-hand side, and XI is going to be the solution. So now what I need to do is figure out how to do what I described, which is take a problem on the fine mesh and move it to the coarse mesh. That's called restriction. I'm going to somehow figure out, I'm going to be a mathematical operation restricting my fine problem to my coarse problem. Then I have to do some work and actually, improve things as much as I can on a particular mesh. That's going to be called the solution. And then once I get the solution in the coarse mesh, I have to put it back on the fine mesh, and that's called interpolation. So I have these 3 different operators, and they're all turn out to be just averaging with your nearest neighbors, just different values of averages. So here's the restriction operator. So that's where I take my fine problem, and I restrict it to the coarse mesh. So it maps pi to pi minus 1. That's fine. That's coarse. And so to do that, I have to take my right-hand side. This is basically what it does. It takes my right-hand side, my problem, and it approximates it by something coarser. So it takes in this vector, does some averaging with nearest neighbors, and gives out this much shorter vector, half as long. Then the interpolation goes the other direction. These 2 operators are just almost the same as one another, almost inverses. So it takes my solution on the coarse mesh, I minus 1, and gives me my approximate solution on the fine one. And so on mesh I. And I'll write it this way. So the interpolation operator maps from I minus 1 to I, x sub I minus 1 to x sub I. And so that's also going to be just averaging with neighbors. And then I haven't actually done any work yet to actually improve the solution. So finally, I have a solution operator, which just works on one mesh size and it's only allowed to talk to nearest neighbors on the mesh, and so it can only get rid of some of the error. So the question is, which part of the error can it possibly get rid of? And it turns out that it's going to get rid of what's called the high-frequency error. That's the only thing you can see when you can only see your nearest neighbors, sort of things that change rapidly from one neighbor to the next. That's all you can get rid of. And I'll show you pictures. So now we have enough notation to write down the whole algorithm, even though, and even know how fast it runs, even though I haven't told you what these operators actually do. I mean, I've told you they average with their neighbors. I haven't told you how they average. We don't need that yet. So here's the whole algorithm on one slide. And it's recursive. It's called multigrid v-cycle, for a reason I'll explain, MGV. And here's the function, and it calls itself, right? It's recursive, so here I'm calling it on the fine grid. And here it calls itself on the coarse grid to solve the next problem. So all the work is the fact that it's a recursive function. So it's going to solve my Poisson equation on the grid of mesh I, and it passes in, what's it pass in? The right-hand side, and my solution, my initial guess, which could be 0. I could start with anything. If I'm already down to the 1-by-1 problem, well, I just solve it. I'm done. That's the base of the recursion. Otherwise, I have some work to do. So I start by running my solution operator. I do a little bit of averaging with my nearest neighbors to do what I said, which was get rid of the high-frequency error. That's all you can do when you talk to your nearest neighbors. Then I compute the residual. If I had solved it perfectly, the residual would be 0, but that tells me what I have left to do. Now, the interesting part happens. I take my residual, I restrict it. So I take this problem, and I restrict it so now that it's on the coarser mesh. So now I'm going to solve a problem in the coarser mesh. That's what the big R does, restricts. And I'm going to call the multigrid algorithm again. What's my starting guess going to be? I don't really have a good guess, so I'll just guess 0. So that's my starting guess. And so I run it. I solve the problem in the coarse mesh. And then I interpolate it back to the fine mesh. And that gives me a correction. So this, I have now solved Tx equals r, and I've gotten d by calling it recursively. And I just take that correction and I subtract it from my solution. And if I've solved this coarse problem correctly and interpolated it back, that should fix all the errors in x. But it doesn't quite fix it perfectly, so I better get rid of a little bit more high-frequency error, and then I'm done. I return that answer. So that's all you need to know, except, of course, what do these operators do? But they do some averaging with their neighbors. So, and I'll show you that with pictures. So why is this called a V-cycle? That's a funny name. It's really just a picture of the call graph. So let me just draw a V and explain why this is called a V-cycle. So here is the horizontal axis is time. So this is the algorithm executes, marches from left to right. And this is the level of the grid. So 5 is the finest grid. 1 is the coarsest grid. So I start by calling the algorithm on the finest grid. So that's problem 5. And it calls itself recursively on problem 4 to solve the coarse grid. Problem 4 calls itself recursively on graph 3. Graph 3 calls 2. 2 calls 1. And finally, I solve it. It's a 1-by-1 problem. And then I start returning. I use my solution on my 1-by-1 mesh as my starting guess for the 2-by-2, starting guess for the 4-by-4, starting guess for the 8-by-8, and so forth. So that's why it's called a V-cycle. It's just kind of a picture of which algorithm, how they call one another, and how they return. Now we know everything we need to know to write down the complexity and to prove that this algorithm is optimal. And I haven't even told you what the averages are with the neighbors. It doesn't matter. It just, all you have to know is that you talk to each neighbor. You got 4 neighbors. And you do a constant amount of work with each neighbor. And in a big O sense, that's all we need to do to understand that this is an optimal algorithm. So here's how we count the work. It's very simple. And I'll do it just on a serial machine. And then I'll tell you in parallel. And then later, when we look at the real algorithm, I'll do a much more careful analysis of its complexity in terms of how much it communicates. But on a serial machine, let's just ask ourselves, let me go back to the algorithm here. At each level, what am I doing? I average myself with my nearest neighbors a few times. The amount of work is a constant per mesh point. So this just costs how many mesh points I have. This also is just averaging with the nearest neighbors. This is cost proportional to the number of mesh points. Now I do a recursive call. And this is constant work per mesh point, do a subtract. And this is, again, just averaging with mesh points. So this whole loop is just the work is proportional to the number of mesh points plus this recursive call. OK, so let me just write down how many mesh points do I have at level I. Well, it's a 2 to the I by 2 to the I mesh. So it's 4 to the I mesh points. And that's how much work I do. So I do that at every level. And it's recursive. So it calls itself. I do 4 to the m, then 4 to the m minus 1. At the next course, 4 to the m minus 2. It's a geometric sum, really easy to solve. And it's just proportional to the number of mesh points in the finest mesh. So that's linear, right? I'm doing a constant amount of work per mesh point. It's just a geometric sum. Because each level costs me a quarter of as much as the previous level. So all the work basically is done on the finest level. And that's optimal, the number of unknowns. Now on a parallel machine, so does that make sense? So geometric sum. On a parallel machine, if I have as many processors as I want, 1 processor per mesh point, then that takes me time 1, right? Everybody talks to their neighbors and gets the data, and that costs me time 1. So each of these lines of code is time 1. So the whole inner loop is time 1. So the only question is, how many times do I call myself recursively? Then I multiply that by 1, order 1. So how many times do I go through the loop? How many recursive calls are there? If I start with a 2 to the m by 2 to the m mesh. So it's 2 to the m by 2 to the m, and then it's 2 to the m minus 1 by 2 to the m minus 1. And then it's 2 to the m minus 2 by 2 to the m minus 2. M, yes, right. I go do it m times. And m is just the log of the number of unknowns, right? So that's how many steps it takes in this perfect PRAM model. Now, when we don't have an infinite number of processors, but P processors, I'll write that down later, too. We'll see how long it takes. But the speed up is perfect, almost. OK, so that was called a V-cycle. And for completeness, and to state the theorem that says this is an optimal algorithm, I'm going to use that as a subroutine. So the thing I just told you is a subroutine. And that's a subroutine that I'm going to call in full multigrid. And all full multigrid is going to do it's going to solve the problem on a 1-by-1 mesh by calling the algorithm I just did. Perfect solution. It's going to use that perfect solution on the 1-by-1 mesh as a starting guess for the 2-by-2 mesh. It'll solve that calling the V-cycle. It'll use that perfect solution on the 2-by-2 mesh as a starting guess for the 4-by-4, and so forth. And that's exactly what I do. I just start from the coarsest to the finest and solve that problem and use that as a starting guess for the next level. So again, it's just a geometric sum, and all the work is done by one V-cycle at the finest mesh. And if you make me draw the picture of the call cycle, this is what it looks like. I solve the 1-by-1 problem, use that as a starting guess for the 2-by-2, and that gives me that little V. I use that as a starting guess for the 4-by-4, that gives me that V. That's a starting guess for the 8-by-8, that gives me that V, and then the starting guess for the 16-by-16 gives me that V. So again, it's just another geometric sum, and it's all proportional to the number of unknowns. All the work is done in this last V cycle. These other V cycles, are smaller by factors of 4. So all the cost is perfect. Well, now except it's log squared, but that's OK. So what's the theorem? The theorem says that if I do that algorithm I just showed you and run it once, the error always goes down by a factor of 2. It doesn't matter how big the grid was. So I could have had a 1,000 by 1,000 mesh, or a 1,000,000 by 1,000,000, or a 16 by 16. I always get one more bit correct. So how many times do I have to run the algorithm? Well, how many bits do you want? That's independent of the problem size. And so that's why we can call it optimal. So you tell me what final error you want, and I'll tell you how many steps you have to take. And that's some constant number. It can't be more than 24 in single precision, say. That's how many bits you got. And so the complexity is linear in the problem size. OK? So that's the nice property that this has. And proving that theorem is a topic of a different kind of class. But now that's all we need to know. Any questions about the overall properties? Because now I'm going to go back and tell you what actually are the operators. What are the averages I take with the nearest neighbors and so forth? OK, they're all very simple. So I'll start with the solution operator. And so remember, what this does is it takes my solution guess on a fixed mesh, averages with the neighbors, and gives me a slightly better guess. And I'll do it in 1D. And so here's what Jacobi would do, just to remind you. Jacobi takes this particular average with my values on my left, my value on the right, and the right-hand side right in the middle. And all I'm going to do is change that 1/2 to a 1/3 and throw in the value in the middle. That is what it does. Now, so this is, again, just a constant amount of work. It's just slightly more expensive than what pure Jacobi would do. So what properties does this have? Let me just show you a picture to show you what it does. So I'm going to show you kind of a convergence picture of this algorithm running. And so I have 3 steps here. And what I'm trying to converge to is this nice smooth sine curve. That's the true answer. But what I've got is this jaggy line. That jaggy line is the solution. So here I've computed that error. I've subtracted the smooth sine curve from my approximation. I get the jaggy line. And what I'm going to do is going to take one. And here I have the same error, except I've taken its FFT. So here's the jaggy true error. There's the FFT of the jaggy true error. So now let me just take one step and look and see what happens visually. This looks a little bit smoother, doesn't it? This was the original error. I've taken one step. I've talked to my neighbors. I've made it smoother. That's the name of the operator. It's S for smooth. What happened to the FFT? The high frequency of the components of the error got a lot smaller, didn't they? It's getting rid of the high frequency error. Let me take one more step. Here's the solution. The error. It looks smaller still. And now there's almost no high frequency error left at all. The upper half of the high frequencies are pretty much gone. In fact, they've been multiplied by about 1/9. That's how fast it works. So that's the intuition behind what it does. The same thing is true in 2D. It's easier to see it all in 1D. It kills the top half of the error measured in frequency space. It makes it nice and smooth. So now what I do is when I take every other mesh point, it's not going to look smooth anymore. It's going to look just coarse again. So that's what it does. Let me just draw the picture another way. So you could think of this as doing domain decomposition. Or I'm sorry, let me take that back. You can think of this as doing divide and conquer. So what did I just show you? Here's the frequency space. And what I just said is here's all the upper half of the FFT, and this is what I zapped. I made all of those high frequency errors go away. Now what happens when I go down to the coarser mesh? I can only see the bottom half of the frequencies. That's what happens when you only take every other mesh point. You can only see the bottom half of the frequencies. So everything is down here. What happens when I smooth here? I get rid of the top half of whatever's left. I get rid of these high frequency errors. So now all those errors are gone. I coarsen it again. All I can see is that much of the original frequency space. I get rid of half of that again. So every time I call multigrid, I get rid of half the errors, half the high frequency errors that I didn't have before. So that's, not going to do the math, but that's the picture that you should keep in mind, whether it's in 1D or 2D. So that's what the smoother does. And let me just say that in 2D, there's a similar average of your nearest neighbors. You just have to pick the weights correctly, and it'll get rid of the high frequency errors in 2 dimensions. OK, so what about restriction? This is much easier. So what do I have? I have a solution which is defined on a whole bunch of mesh points here, 16. So it's all of these little, this dotted line. And what do I want? I want to get a coarse approximation. I want to get this solid line, which is only defined in every other mesh point. So what's the obvious, simplest thing to do? I can just sample, right? I can just take every other mesh point. That would be the easiest thing to do. Just throw away the ones except every other one. It turns out there's a slightly better way to do it, which is just to average with your nearest neighbors again. So here's where here the coarse approximation is I just take every other mesh point. And here, I take a particular average with my 3 nearest neighbors. So that guy is the average of that one, and that one. This guy is the average of that one, and that one. It makes it a little bit smoother. And they're the weights. A half times my mesh point and a quarter times my neighbors added all together. And this turns out to be the right way to do it. And again, it's just nearest neighbors. And there's a similar formula in 2 dimensions. Look at all your nearest neighbors to the north, south, east, and west. And then there's interpolation. That's where I have a solution which is only defined on the coarse points, every other point. And I want to define it at all the intermediate ones. And here, your intuition is, well, just connect the dots. And that's all you got to do. So all I'm going to do is, the value in the middle will just be the value on the straight line, connecting the dots. It's the simplest thing. And it works. And in 2D, you have to be a little bit more careful. So if you're in the middle here, you have 4 neighbors, and you have to average them appropriately. But it's almost like drawing a straight line. So those are the operators for smoothing, and for restriction, and for interpolation. So if we put it all together, let me just show you how it converges. So here's a convergence plot, just to see what goes on. So here is the true solution, which is I've chosen something a little bit difficult. So it's this piecewise linear curve. And here is the right-hand side, which is like a delta function. So it jumps up to +1, jumps down to -1, and it's 0 everywhere else. So what I'm going to show is how it converges. So here I have a plot of the error for after the first iteration, second, third, fourth, fifth on a log scale. And here I am plotting the ratio of the error from one step to the next. How much smaller does the error get? So it's the ratio of the ith error divided by the I minus first. And here is the error, again, on a log scale, just the norm of the error. So the norm of the error is a straight line with a slope going down. That tells me I have a constant convergence rate. What's the slope of the line? It's about 0.2. So every time I run this algorithm, the error goes down by a factor of 0.2. And here you can sort of see it happening in more detail. All of these lines get smoother and smoother. The error gets smoother and smoother. We were expecting that. It started with a very jaggy error. And after I do a few steps, it's nice and smooth. And the vertical distance between the errors looks like a constant, because I'm on a log scale. So it's going down by a factor of 0.2 at every step. So that's the behavior in one-dimensional Poisson, one-dimensional multigrid solving Poisson. And here's a 2-dimensional picture giving you the same idea. Here's the true solution. Again, I just chose a step function to make it challenging. There's the right-hand side, which is 0 in a lot of places with some jumps. Here is the ratio between the errors at consecutive steps. And now the error is going down by a factor of 0.4. So 2 dimension is not quite as fast as 3 dimensions, but it's still as 1 dimension. But it's still better than at least a factor of 2 at every step. And here's another way to look at the same data. I've plotted the error on a log scale going down with a constant slope. So it's all behaving very nicely. And the question? Is the mic on? Good.
So I'm confused about the frequency of the errors. So what would the frequency of the errors be here?
So in this case, if I didn't make that plot, but if I had, I would take a 2D FFT, a two-dimensional FFT. So I'd take an FFT in each row and then along each column, and I'd get a two-dimensional array of frequencies. And and then we would see that that is going down. You know, the high frequencies there would go down.
So the frequencies are just the errors at each point? What are the frequencies?
So let me go back to the one-dimensional case where it was easier to see everything. So here in the one-dimensional case, this is the error, the true error, if you like, the difference between the true solution and not. And here, I took the FFT of this vector, and I'm calling that the frequencies. Right? So here's the FFT. Okay. This function is the FFT of that one. And if I had a two-dimensional problem, I'd take what's called the 2D FFT, about which I will also give a lecture. I guess this is slightly out of order. I will talk about parallel FFTs too, but let me just appeal to your intuition. The FFT tells you the frequency components of something, and you can do it in as many dimensions as you like. But now the question is, how do we parallelize it? And as I said, I'm going to start just with structured grids, nearest neighbors, and then later I'll talk about how it works in irregular meshes. So let me assume, just to draw a picture here, that I have a 32 by 32 mesh, and I have a 4 by 4 grid of processors, which are the bold lines. So each processor here, this is processor 0, 0, if you like, and it owns all the mesh points inside there. And for the finest mesh, I've labeled it 1. And I guess I've labeled it 5. Yes, so that's problem P5. That's the finest mesh. So 2 to the 5th, 32 by 32. Then here, I've labeled the points on the next coarser mesh 4, problem P4. That's every other mesh point. There I've labeled the mesh points P3, owned by that processor, every other mesh point again. And then problem P2, there's only one mesh point per processor. So what happens if I go to the next coarser level? Is every processor going to be busy? No, because at some point in this business, some processors will have no more mesh points. So that's going to, you have to just know that, and that tells us there's some load balancing issues. But let's not worry about that right now. So let's ask ourselves, what is this processor, the pink guy, going to do? What does he do at every step? Well, let's look at the finest mesh, where all the points labeled 5, which I haven't drawn in here. You have to get your nearest neighbors and do some averaging with your nearest neighbors. So if the processor owns a mesh point here, he has to get the nearest neighbors to the top, bottom, left, and right. And he owns them all. There's no communication. What if you're on the border? What about that point? You got to get your neighbors from the left, right, bottom, and above. That is owned by the processor above you. So all of the points labeled 5 on that border have to be sent from this processor to that processor to take a multigrid step. The same thing with the points labeled 5 here, here, and here. OK, so that gets us through one layer, the finest layer. Now we call multigrid recursively, and I'm going to do the same thing for the points labeled 4, every other mesh point. So that point, and that point. If I'm in the middle, again, my 4 nearest neighbors, the ones that are 2 away in each direction, I own them all, no communication. But now, what about this guy? 2 of the neighbors labeled 4, two grid points away, are owned by the processor to the left and the processor above. So there's communication. So all the points labeled 4 here are on different processors. And again, I have to communicate with my neighbors to get those. Next coarsest is 3. Again, I have to talk to all my neighbors to get half as many points now, but labeled 3. And finally, when I'm at the coarsening level 2, I only need one number from all my neighbors, all those little points labeled 2. And then finally, if I keep going, some processors are idle. So at every step, I need to talk to all my neighbors for a while until I become empty, perhaps. But at each step, I need to get half as much stuff from every neighbor. So it's easy to write down all the formulas for how much I have to communicate, geometric sums. It's all simple. And so let me just say what that is, and then I'll put up a little table. So I'm going to start with a mesh, 2 to the m plus 1 by 2 to the m plus 1. And I'm going to assume that I have a grid of processors. And to make all the counting easy, it's going to be a 2 to the k by 2 to the k grid of processors. So here, m was 5, because it's a 32 by 32 mesh of points. And I have 4 by 4 mesh of processors. So it's So it's a 4 by 4, or so K is 2. So that's the processor mesh. And so I'm going to do my V cycle. And so at each level, I'm just going to say, with whom do I have to communicate? Well, and how much work do I do? The work I do is a constant amount of work for every point that I own. So it's just a sum, 4 to the j minus k. I have to talk to each neighbor. I have to send one message. That's the latency of a message. We call it alpha. So one message to each neighbor, and there's a constant number of neighbors. And how much data do I have to send? Well, you just count the number of blue points, red points, et cetera. And again, it's a nice simple formula, 2 to the j minus k. And so I need to sum that. And once I get coarse enough, then my neighbors only have one piece of data, perhaps, and they're farther away. Then it's just a constant. All these turn into order 1. So finally, putting it all together, here are the formulas for the complexity. So what do I have? I have the formulas for multigrid, for FFT, which I haven't done yet, but we'll do it next time, and for SOR, the algorithm I talked about last time, red-black SOR, where I only talk to my nearest neighbors and average them. And I'm going to compare how many floating point operations do I do, how many messages do I send, and how many words do I send. Those are my 3 components of the cost. Each of these gets multiplied by some machine parameter. And so if you look at the flops, multigrid, I'm going to do n flops, and I'm going to do it p times faster. Right? This is perfect. This term all by itself is perfect speed up. Each processor does one piece of the flops, but there's some extra work, and so there's a log term. Right? So it's not absolutely perfect, but it's pretty close when n and p are large. FFT is almost perfect. It's n log n over p. And the SOR is much worse, n to the 3 halves over p. So this is still perfect speed up, but it's doing a lot more work. It's doing n to the 3 halves. What about the number of words sent? Let's look at that next. So here I have n over p, the square root. And that's a whole lot better than either n over p or n over p. Right? So this one, so multigrid wins there too. Again, there's a log term. And the number of messages gets interesting. These are not so comparable. It's not utterly clear whether log n squared beats p to the 1/2 or not. And so it kind of depends on your problem size and so forth. And so the takeaway is that it's not clear whether multigrid or FFT wins. They're almost certain, they're both going to beat SOR, except maybe for super tiny problems on one processor. But on a big machine, it depends on the parameters. How much is a message? How expensive is a message? If that dominates, then it gets more interesting. If the flops dominate, multigrid wins. If the bandwidth dominates, multigrid also wins. OK. So let me just put up a few performance numbers. I'll start talking more about practical implementations now. So we don't usually go all the way down to a 1-by-1 problem. That's kind of a waste of time, because once a problem gets small enough that it's sitting on one processor or just a few, you might as well solve it a different way, in a more direct way, instead of, because there's just too much overhead for doing that. Now you might say, isn't that, who cares how we solve the coarse problem? Because isn't that like a huge power of 4 smaller than the finest grid? Why do I care about that very tiny term? Well, the constants matter. And so let's suppose we get down to 1,000 points per processor on 2D. So a processor owns 2D. So I want to compare how much it has to communicate, which is 1,000, with how much it has, how many flops it has to do, which is 1,000 mesh points, compared to how much it has to communicate, which is the surface area, right? So I have a square. It has 1,000 points in the square. How big is the boundary that I have to communicate? Well, the square, what's its dimension? It's the square root of 100 by square root of 1,000 by square root of 1,000. It has 4 neighbors. It's about 128. So there's 128 words to send, which is, about 13% of 1,000, right? So the border is not a trivial fraction of the work. But what about in 3D? So I have 1,000 points in 3D. That's a 10 by 10 by 10 mesh, right? How much boundary? How big is the boundary? Half. So the communication is actually a large fraction of the number of flops I have to do. So communication is really going to dominate there. And so we don't want to go all the way down to 1 by 1, right? You can imagine, even 1,000 points, communication may be dominant. So here's some data, both very old and very new, just to show you the problem's been around for a while. So this was a mere 1,024 processor machine back in 1993. And they did a 64 by 64 grid and a 1,024 by 1,024 grid on it. And when they finally, there are only 4 unknowns per processor, right? So this is a very coarse grid. And the efficiency was 2% because it spent all its time communicating. And when it went up to 1024 by 1024, it finally got decent. It was, the efficiency was 0.7 or 0.42, depending on whether you were looking at a single multi-grid cycle or full multi-grid. And this machine was easy because this machine had really slow processors and really fast communication back then. Now it's much worse. And in fact, Chombo, which is the project on which your teaching assistant Brian works, has this problem in spades. And there's a project going on right now to say, can we minimize the communication in solving the coarsest meshes, the coarsest grids, by doing something completely different than they do now. So it is the bottleneck. And there's a class project probably available in that. So that's what I wanted to say about one practical issue, which is you don't go all the way down to 1 by 1. Something interesting happens. And the next practical thing I want to say is that we don't always work on perfect meshes. But real meshes are a little bit more complicated. So in particular, what people often have are adaptive meshes, where because you don't care. So here is an example where you might be solving Poisson's equation to get the electrostatic potential around this molecule. And you need to know what it is so you can tell how it moves. That's a pretty important thing in molecular dynamics. And here, where there's no atoms, you don't need to get a very fine resolution of what the potential is. You need to have a very good solution in the neighborhood of where all the atoms are. And so this is what your mesh might look like that I've superimposed. I have very fine meshes here because I need a lot of accuracy. And over there, I don't have much accuracy. And so what I need to do is have multigrid adapt. And there are a number of, so this is not the only source of irregularity. I'll show other ones later. So one thing that people do in this business is they say, OK, I'm going to approximate that funny object here but I'm still going to use lots and lots of square or rectangular meshes. I'll just put them down in different places. So if you look at this, it's sort of a union of little local rectangular meshes. And on each one of those, the algorithm I just told you works. I don't have to have, I can just talk to my north, south, east, and west neighbors and keep track of the fact that I'm doing that in this little box and where it's located in the bigger picture. And so you might have, for example, boxes. Each of these is itself a nice structured grid in which you do the computation I did before. But you have to know that your neighbors, when you get to the border, your neighbors may have very different structures and may be located in different parts of the machine. And you have to worry about that. So the data structures in this thing called adaptive mesh refinement, because it's also moving. I mean, you don't just build it once and then it all works, because the atoms that you're trying to follow are moving. And so the meshes where you put down the fine meshes are moving. And so you have data structures like this, where here are your fine meshes. You coarsen them. And then you have to say which processors own them, right? Because once they get coarse enough, it's not clear that the thing is going to be load balanced anymore. So here's a picture where you take the fine meshes, you coarsen them, they get mapped to different processors. Maybe it overlaps different processors in different ways. How do you assign the work to processors? So people have built a lot of software tools to make this easier so that you can just write the work for one of these grids and have everything, all the other work done automatically, all the mapping. And in fact, there have been a number of projects that have worked on this. And so one of the reasons I'm telling you this is that if you choose to do a class project that has to do with multigrid, then that's an interesting idea. And there's a lot of infrastructure that you should not reinvent, that you should experiment with to see, does this work particularly well for my problem that I want to solve? OK, and let me just say we can talk in more detail about what these various packages and tools are if you want to solve it. So that's one way you extend multigrid to more practical problems, which is you just do it adaptively and have lots and lots of rectangular meshes that you put down in the right places. The other way people do it is to have a completely unstructured mesh. So now we're leaving the structured grid motif or dwarf, and this is more the unstructured grid or motif, dwarf or motif. But it's the same idea. It's the same mathematical idea of multigrid, but the idea of averaging with your neighbors gets more complicated because it's not just left, right, up, and down anymore. It can be much more irregular. This is still semi-regular. Just it's sort of one step away from regular. So this was a simulation where this was rubber and this was steel. And it was a finite element simulation of what happens when you compress it. And so there was one mesh out here with one particular finite element model of which knew about which was simulating rubber. And then there was this steel shell on the inside with a completely different finite element mesh, but you still wanted to solve it using the same idea. So it's not Poisson's equation anymore, it's elastics. And this problem had 39 million unknowns on 960 processors, and by being clever, it got to 50% efficiency by doing the right thing. But it required a lot of infrastructure. So the question is, what has to change from the regular mesh stuff where I could sort of write down simple formulas for how do you average with your neighbors? What happens to multigrid on an unstructured mesh? Well, basically, think of that object that I just drew here as a graph. Everybody's talking to their neighbors. And that turns into a graph partitioning problem. We've talked about that to death. And by partitioning that graph, that's going to assign work to subprocessors the same way we've done it before. And so what do I need to do? I need to be able to take my fine mesh that you just saw and come up with coarser and coarser approximations to it. And if it's irregular, it's not taking every other mesh point. That has to be generalized. And I'll show a picture of how that works in the next slide. I need to redefine what it means to restrict from the fine problem to the coarse problem, and to interpolate from the coarse to the fine. Again, it's averaging with your neighbors, but you have to be more careful about how to do that. And then the solution operator, where you get rid of high-frequency error, again, there's more math that has to be done to figure out the coefficients. But again, you're going to be averaging with your nearest neighbors. So here's just a picture to sort of illustrate what it means to pick every other mesh point in an irregular mesh. And so here is a tube which has a certain thickness. And so I have a mesh which discretizes this tube. And when I take every other mesh point using the one example algorithm, this still looks like a tube, basically, with every other mesh point. But as I keep going and making it coarser and coarser, it kind of loses the original geometry. And sometimes that's OK, and sometimes it isn't. If you lose too much of the geometry, it's not a good approximation. And so people do, in their sort of graph algorithms, have to incorporate geometric restrictions so that you still get decent approximations. But this is actually what gets produced for this particular tube. So let me close with one more example, which won a prize. And I showed you this example, I think, in lecture 2 of the semester, so I'm coming back to it now. And this was work with Tony Keaveney and Panos Papadopoulos here in the Mechanical Engineering Department. And their goal was to take a bone like this from a vertebrae and ask, how likely is it to break in an osteoporosis patient? So right now, the way people predict whether an elderly patient who has osteoporosis is likely to suffer a break from a fall is just to measure bone density and then prescribe medicines appropriately. It turns out that's not a very good predictor of whether people are going to break their backs. And so it's much better to do a very detailed finite element analysis of that particular individual's bones, and then you can predict how strong the bones are. So there's a question of where do you get the bones from, right? This is not from a living patient. This is from a cadaver, right? So this kind of science begins by taking cadaver bones and asking, can we get a much better approximation of its strength by doing a detailed finite element analysis? So how do you do a finite element analysis of something like this? Well, you put it in a micro CT scanner, which uses a lot more radiation than a living patient would want, and it creates this complete 3D image of the bone. So this is a 22 micron resolution. It tells you exactly where every cavity in the bone is, because bones are mostly air. There's a lot of material, but it's mostly air inside, and it's the fact that it's this interesting structure that gives it its strength. And so given this, you take a little piece of it and you form an adaptive mesh which completely discretizes every last piece of air. Well, you leave that out, and the bone. And on this, you can do finite element modeling and say what happens if you put a certain force on it, which is what would happen if you fell, right? You can say what kind of force that is and say, would it break? And using this, and this ran 537 million unknowns. This was the largest problem people had solved at that point in 2004 when they won the Gordon Bell Prize at supercomputing for it, on 4,000 processors at 70% efficiency. So this was quite an accomplishment, and it has now become a more commercial venture. You can't, of course, get this information from a patient, but what you can do is get a much lower resolution image from a standard MRI scan, and that turns out to be apparently good enough to get a decent finite element analysis going in order to predict the need for treatment. So anyway, so that's one example of high-performance computing for medical purposes. And that ends the lecture I didn't finish last time on structured grids. Are there any questions before I go on to the next topic, which is class projects? And there's a question.
You've only been doing squares or boxes so far?
For multigrid?
Yeah.
So this is, that's by far the easiest thing to do. Some people use tetrahedra because those are easier to map to irregular surfaces, curved surfaces, and make sure that you model that correctly. I think for this bone, they did use cubes. Getting the surface right, they decided wasn't quite so important. But so multigrid can, in principle, work for any kind of finite element model. The question is, how do you decide how to average with your neighbors? The mathematical approach is something called algebraic multigrid, and it sort of gives you formulas for figuring out how to do the restriction and the interpolation and the smoothing. But a topic for a different course. Unless Brian wants to add to that, since you work in this. Okay.
Fine.
Okay, close enough.
Close enough.
Okay. So let me now switch to class projects, since a number of people had asked for input on that. So I'm going to give you a mixture of high-level advice about how to structure and choose a class project, and then a lot of specific suggestions, both examples that people have done before, just to give you an idea of the variety, projects that are ongoing now or that people are interested in advising right now, either people in our research group or people from other research groups who've sent emails saying they're interested in help on this. So there are a lot of different kinds of projects and that reflects the diversity of the field and the diversity of the students here, right? So I can't remember. I think we have 10 departments represented in the class, and so everybody is going to have a possibly quite different interest in what they want to do for a project, and that's certainly fair game. And so, but basically what you need to do is choose to do one or more of design or program or measure some parallel application or kernel, or software tool, or even hardware, right? If you're from a department in which you're thinking of parallel computing as a tool, then you're very likely to want to take a particular application and parallelize it, work on designing it, maybe programming some of the insides, and measuring how well it does. If you're a computer science student, you may be much more interested in looking at a lower level in this stack that goes from applications to kernels to software tools to hardware and measuring things at that level. They're all interesting and important activities. You can work alone or in teams. And if you look at the web pages, I don't have all the information on my slides, but we have all of the old projects posted, including posters and videos of students presenting them, which you're welcome to do, and who was on the team. And there were some one-person teams, and there were some three-person teams. It was quite a variety. And of course, the reason we posted homework 0 was so that you could try to do some matchmaking. So what I hope you can do is send me a very rough proposal. I picked this kind of arbitrarily, midnight Saturday, so I can read it over spring break and give you some feedback, right? It's a conversation, right? It's not a final deal. And then we can sort of work together on what is a good thing to do, and I'll try to give you feedback then. And then what we will want to do is have a poster presentation, probably out in the hallway here on the Thursday of RRR week. And I will ask that everybody stand up where I am and give a 1-minute wearing the microphone presentation of your poster so we can post that again to inspire future generations. And that will get posted if you agree, of course. And then the final report write-ups would be due later. Okay. So here are a couple of slides on how to organize a proposal. And of course, as I said, this is an iterative process. It all doesn't have to be turned in by Saturday. You can either parallelize an application or compare different implementations of solving an application. You can do the same thing for a kernel. Maybe you're interested in one of those motifs and you have an idea for a better way to do it. You could choose to work at that level. You might be interested in software tools. I mean, we've talked about debugging and compilers, and there's just all and schedulers and message passing systems. There's just all these sort of tools that we need to have run well, and you could be interested in working in either building or evaluating something at that level. And then, of course, there's all the way down at the hardware, because all of these machines have all these monitors in them that say, where is the time and even the energy actually being spent in a particular application. And you could work at that level and work and ask, what can I improve, or where the real costs are at that level. It's all fair game. You don't have to do all of them. So what I would like to see is a list of the tasks that you'll try, sorted in order from low-hanging fruit to gee whiz. It would be nice if I could do this someday. So chances are you'll only do a few of the things on the beginning of your list, but it's nice to have sort of an inspirational vision that you'd like to do someday. So it would be good if you knew what tools there are out there, because it's not good to reinvent wheels unless you think you can build a better wheel. I mean, that's a fair game too, but don't say, I need to do graph partitioning. I better invent graph partitioning. Right? No, go ahead and use one of those things. Right? So for applications, if you're working there, you don't necessarily want to write it in a language like C plus MPI or CUDA. You might want to go up a level. And because there are a bunch of frameworks that people have built, including one that Brian works on, and other ones like PETSI, which are intended to let people program at a higher level and still access a lot of parallel libraries and so forth. We are going to have a lecture on these frameworks, programming frameworks, later in the semester. Scheduling has meant that I haven't gotten it into the class so far. But if you want, you can look at last year's lecture. It's all posted, both the video and the slides. It's lecture 23 from CS267 last year. And it's the same expert, John Shelf from Lawrence Berkeley Lab. So if you want to hear about what these tools make available to you, you can go look at those things and ask yourself, if you're doing an application implementation, do you want to use one of those? And then what I'd like to do, and this is maybe more for the final write-up, is if you do an application, we've given you hints about there are all these tools for reuse, like computational patterns, dwarf structural patterns. Which ones did you use? Which ones are the natural ones in which to decompose your application? And then finally, how do you know when you win? What are your success metrics? And other than I finished writing it up in time, so that's important too. So you'd like to say, I want to solve a particular science problem. There's a particular application, and here's the size of the problem that would tell me something new. How fast did it run? What is the speed up I got on how many processors? Is it close to being what you expect? And you might want to also propose to collect a certain amount of data from performance monitors or IPM or any of those tools to compare or evaluate different approaches, but something quantitative to sort of indicate how well you did. So here are just a few. Now let me give you a long list of class projects. Here are a few which are particularly fun. This is from 2009, which is the last time I had people speak and do a video to do their class projects. And it's all posted there. So the first one is content-based image recognition. This was a beginning Parlab project at the time. And the motivation is, many people have cell phones, take cameras. With cameras, they take pictures, and they'd say, here's a picture of my cousin Fred, and here's another picture of his friend Susan. Find all the pictures of them standing together. Right? This is a large search problem, and the question is, how do you parallelize all of the image segmentation and other stuff going on in there? There was another example from Better Molecular Dynamics, and I think that in this case they were doing a protein called amyloid beta peptide, which is goes through a certain chemical process, and it's related to Alzheimer's disease. So they were trying to parallelize a particular kind of molecular dynamics calculation there. Another project that's Parlab related was speech recognition. Siri has not solved all problems. There's still lots of interesting questions about doing better speech recognition, and they were trying to do something, I think, with a hidden Markov model inference engine to do a more accurate job of recognizing speech. There was another person who was trying to figure out how to take data that new genome sequencers are producing, which are apparently a lot more error-prone. I mean, they produce vast amounts of data, but it's not as high quality as it was before. And they needed new error filtering algorithms, which they implemented on a cloud, and apparently made the data much more useful. A marine biologist was trying to simulate zooplankton population. So there was a mixture of an ocean model and a biological model, and it has to do with predicting the health of coastlines. And then this one, the last one, was fun because it recognized that if you're trying to play a game on your cell phone and you don't have enough bandwidth, so it doesn't work very well, but you're standing around in a crowd of friends and they all have their cell phones, why can't you use their bandwidth? right? And parallelize, in this case, the communication over the telephone network or whatever, the wireless network, to have a better experience. I think they talked to a venture capitalist when they were done with the class, so you can imagine that it's more commercial interest, but it's all fair game. So which of these teams do you think was the undergraduate team? The last one, playing games on cell phones. Yes, right. Okay, but that's just perfectly fine. So let me just give you, with a little less detail, some more prior projects. So this is a list from, again, that same semester. So there's a little overlap with the list I just gave you. So the first one is related to the image segmentation problem in the Parlab. The next one has to do with graphics rendering. You take two images and you want to compute the sum of those two images. That's what a Minkowski sum is, and do that without doing n-squared work. This is doing feedback control on nonlinear systems, which requires sort of statistical sampling of a nonlinear filter, sort of a nonlinear Kalman filter. The next one was the image retrieval problem. I mentioned that one already. How do you search large databases of pictures? The growing string method, I believe that was another molecular dynamics kind of problem where you're trying to say, electronic structures problem where you're trying to predict whether a certain reaction will occur. And so you're trying to find a path through a minimum energy surface. The next one was very closely related, what I was just talking about, Poisson operator and Chambo, so for doing multigrid. Sparse matrix vector multiply on GPUs, we've certainly talked about that one. This one was Hartree-Fock, so again, a molecular dynamics simulation, trying to make that go faster. Parallel FFTs in 3D. You haven't heard that lecture yet, but there's a big design space about how to make 3D FFTs work better. This next one was actually the problem, the person who was working on amyloid beta peptide for Alzheimer's disease. This was the technical detail of how she was doing the molecular dynamics. This is the speech recognition problem using hidden Markov models. This was using a parallel Krylov subspace solver for solving large, stiff ODEs. This was the person who was doing the cloud implementation of filtering errors out of these new genome sequencers. This project was the undergraduates who were trying to get their cell phones to share bandwidth. The next one was also, I think, molecular dynamics related, using multipole algorithm for solving Poisson-Boltzmann to get the forces on all the molecules you're trying to push around. The next one was mechanical engineering, finite element parallelization, comes up in lots of places. Parallel Grubner basis, that's a sort of a more pure math problem. Gaussian elimination is elimination on linear equations. Grubner basis is the same idea on nonlinear equations, where you have polynomials. It's rather more complicated to explain, but that's the idea. There's lots of parallelization there. More molecular dynamics. This next one was actually a sort of a third world medical application, detecting sickle cell anemia quickly by shining light through blood samples, and depending on how it refracts from the blood, it comes through in different patterns, you can say whether the blood cells have misshapen, which is the detector of that. So the question is, can you get that into a small device? NURBS are for, let's see, that's for nonlinear surface approximation with polynomials and rational functions, and doing that quickly for rendering images. Trying to understand why you run MapReduce at 2 different times. It takes vastly different amounts of time trying to understand how the scheduler in MapReduce could be improved to make it more reproducible. The next person was more commercial. So suppose you have a browser and it's running lots of little background functions to put up images or to make sounds. How do you have that be automatically parallelized using virtual machines running on different cores so your desktop applications run faster? This is one of the more lower level computer science problems, looking very carefully at all the multitude of performance counters and asking how well do they really tell you what's going on in your application, how you used to tune it. The next one was motivated by the fact that a big use of energy in this country is data centers. And the question is, can you reorganize the way those MapReduce and other applications are implemented in huge data centers so they use less power? I mean, right now they build them out in the middle of nowhere next to power plants because the power is so expensive. So that's an important optimization. A linear algebra problem for the symmetric eigenvalue problem. And the last one, Popsicle. That was the zooplankton application, trying to understand how plants grow in the ocean. Okay, so that was just prior projects to give you an idea of the diversity. So I have a few more slides, which are just repeats of ones I've given before, which are ones that I'm particularly interested in, so you can choose to work on them or not. But here's sort of a general pattern. You could pick one of the motifs, one of the dwarfs. There's a lot of them. You could pick a target parallel platform that you're particularly interested in, be it multi-core or distributed memory. You could pick a parallel programming framework, and here I happen to list them all for dense linear algebra, different ways of parallelizing it. And then you could design an algorithm, implement it, measure it, and compare it to the other existing implementations. And you can do that 13 times, right? There's whichever motif you happen to be interested in. That's sort of a general pattern for doing a class project. So for sparse linear algebra, we have weekly meetings where we discuss all sorts of different design issues. It's called BBOP, Berkeley Benchmarking and Optimization. And if you want to come, if you are interested in coming to these, then we can talk about sparse matrix vector operations and different architectures, on how to do the communication avoiding version, which I talked about briefly here, how to speed up particular matrices of interest, and there's lots of sort of compiler technology, sparse polyhedral framework that people are inventing to make this stuff go fast. So if you're interested in the compiler version. This suggestion was emailed in by a staff scientist at Lawrence Berkeley National Lab, Sherry Lee. She's the author of a very widely used sparse linear equation solver called SuperLU, which scales extremely well for solving sparse linear equations. It now has a bottleneck as they try to scale up more, and she thinks that there's a way using some of our new communication avoiding algorithms that bottleneck can be removed. So she's suggesting that in collaboration with her, you could instrument the code to evaluate is this really the bottleneck that she thinks it is, by doing a bunch of measurements using these performance counters, and then try to insert the tall, skinny LU algorithm that we talked about briefly to see if that removes the bottleneck. So anyway, that's another one. This one was proposed by Oded Schwartz, who's a Parlab postdoc. And there's a pattern for parallelization which has come up so many times that it seems to be time to automate it using this system called CJITs, which is selected just-in-time specialization, where you write the code in a very high-level way, Python, and then you say, use this idea of, I'm going to traverse this divide and conquer tree. I'm going to do it in a breadth-first fashion, as long as I have enough memory and processors to spawn a separate process for each leaf, each child of a tree. And finally, when I run out of either memory or processors, I switch to depth-first search. Processing of the tree. This turns out, if you do it right, leads to provably optimal algorithms for a variety of linear algebra problems, but it's come up so often, it seems to be the right kind of thing to automate, so that somebody can just say, here's a divide and conquer algorithm, please use this pattern of switching between breadth-first search and depth-first search to automatically parallelize it. Oded also suggested a bunch of other fast matrix algorithms in which we've been working both for dense and sparse linear algebra. So last semester, we taught a special CS294 course on communication avoiding algorithms, and a number of people participated in that and came up with new algorithms. In particular, Derek discovered a new algorithm which is provably optimal for multiplying long integers. So it does the minimum amount of arithmetic and it does the minimum amount of communication, and he wrote that up as a theory paper. And it's now would be interesting to go actually implement that. It requires large FFTs and things like that. So that would be an interesting thing to do. And the last one is something that's just come up in the last few weeks as we are preparing a large proposal, which is the bottleneck in a lot of computing is not going to be time directly. Time is very important, but it's the energy it takes to actually solve the problem. And of course, time and energy have a lot to do with one another. So the question is, can we come up with provably energy minimizing solutions for a lot of the different problems we have? So that requires understanding what is the model of the cost of doing a floating point operation, of storing something in memory, of sending a message from one processor to another. And we have a few examples where we can actually provably minimize energy. And so what would be interesting, and we also have a few devices, parallel machines in the lab with energy counters on them that actually measure how much energy they use. So it would be quite an interesting experiment to actually see if we can measure what we predict is true. Okay. that's probably enough projects. You probably have a few more in your minds, too. Are there any questions? Yes? Here.
Will it be a problem if we can't make it to the poster session?
So, people have other obligations. So as long as you maybe send me your poster, and we can post it and people can look at it, that would be fine.
Okay.
Okay. Any other questions? Oh, yes.
For the proposals on Saturday, do you want a full team listing, or is that to come later?
It would be, so if the team changes, then that means I will have gotten a proposal from somebody else who then changes teams, presumably. I guess, yeah, it's called the stable marriage problem. It's sort of a well-established. So the more stable it is by Saturday, the better. But I understand if people change their minds. Okay. So I think there's actually enough time left, because I only have 7 more slides, to finish one proof that I didn't do before, which is why the algorithms I talked about for the linear algebra, for dense linear algebra, are optimal, why they hit the lower bound. So let me just finish with that. It should be easy to do in the little bit of remaining time. Okay, so this is what I claimed before. So let me just remind you of what it said, and then I will, in a few slides, prove it. So what I want to do is direct linear algebra. So just think matrix multiply. I have 2 n by n matrices. I want to multiply them, and I want to communicate as little as possible. And so the easiest way to think about it is that I have a large matrix. It's too big to fit in my cache. My cache is of size m. And what I want to do is minimize the amount of data that moves back and forth between DRAM and cache. And so m is the cache size in the sequential case, and it's the local storage that I have on each processor. Each processor is going to, if I have p processors, each processor is going to own 1 piece of the matrix, so n squared over p. And so the number of flops is going to be the number of flops done per processor. In the sequential case, it's n cubed. And in the parallel case, it's n cubed over p. And here was the claim that I made before. No matter how you organize those n cubed operations, then each processor has to move at least, that's lower bound, however many flops it does, divided by the square root of its local memory. And that is, so that's a lower bound, and we talked about how to attain it before, but we didn't prove that that was actually, couldn't do better. And so that's one metric that's very important. The other metric is, how many messages do I send? Well, you take the number of words and you divide by the largest possible message. The largest possible message is your whole memory, so that's a factor of m smaller. But all the work is really just in this. Why is it that I can't possibly do better than the amount of arithmetic divided by the square root of my local memory size? And so that's what I wanted to prove. And so here, just to remind you, here's a sequential case. The number of flops is n cubed, and m is the cache size, so it's n cubed over m. In the parallel case, with n by n matrices spread over p processors, if it's load balanced, every processor is going to do n cubed over p flops. And there's going to be 1 copy of the data. Every processor owns an equal amount of that. So the local memory is n squared over p. So if I plug that's n cubed over p, that's n squared over p, this is equal to the number of words moved. And there's the number of messages. So those are the 2 lower bounds. And the question is why? And it's a nice, elegant, simple proof. So I just thought I would finish that topic. So here's the idea. Think of the program, think of the sequence of instructions that a processor executes. So it's going to do some loads. That means bring data into my fast memory. It might do some loads, and it might do an arithmetic. And then it'll do a store. That means put the data back. So the red boxes here are communication, moving data from fast to slow memory or from slow to fast. And the blue ones are arithmetic. So whatever your algorithm does, it looks like this, right? So I need to reason about it. So and time goes down. So that's the first operation, that's the second, that's the third. So what I'm going to do is I'm going to take that sequence of operations, whatever it looks like, and I'm going to break into something called segments. What's a segment? I'm just going to count the number of loads and stores, the number of data movements. And as soon as I count up to m, the fast memory size, here m equals 3, I'll call that a segment. So these 3 belong to a segment. These 3 belong to a segment. Those belong to a segment. So segments, the only thing they have in common is they contain exactly m loads and stores. So I'm going to reason about segments. So what I'm going to do is, so this is a proof that goes from 2004. And what I want to do is, and this is just repeating in English what I said on the previous slide. I'm going to take that instruction stream and break it into segments. It looks like loads, stores, floating point operations. So what I need to do, and this is the elegant part, the hard part, is I need to come up with an upper bound on how much work I can do in each segment. So if I know that in this segment I've done 1, 2, 3 loads and stores, how many floating point operations can I do? Why do I think that I can bound that? Well, if I know how much data I have, I should be able to say how much useful work can I do. So somehow I have to figure out how to do that. So I'm going to call that F. Capital F is the amount of useful work I can do, given that I have m data available to me. OK, so now if I multiply the most work I can do per segment times the number of segments, that's going to be bigger than the total amount of flops. Right? That's an upper bound on the flops per segment times the number of segments. That's an upper bound on the total number of flops, which is, I'm doing matrix multiply, 2n cubed. So the number of segments is bounded below by the total number of flops divided by the most work I can do in a segment. How many loads and stores do I do? That's the communication. Well, a segment is defined by I've done m loads and stores. So the total number of loads and stores is m times the number of segments, which is bounded below by m times the number of flops divided by the maximum number of flops per segment. So it all comes down to, can I get an upper bound on F? And that would give me a lower bound on the number of loads and stores. So what was my goal? My goal was to get this to be t divided by m to the 1/2. That was what I claimed it was for matrix multiply. So what is F going to be in order for this to look like t divided by m to the 1/2? It's going to be m to the 3/2. And that'll cancel the m, and I'll get t divided by m to the 1/2. So somehow, for matrix multiply, if you give me m words of data available, I have to prove to you that I can't possibly do more than m to the 3/2 useful work. So how am I going to do that? Let me just go to the picture. I'm going to represent all the work I do by a cube, where each cube is indexed by I, j, and k. So what's the inner loop of matrix multiply? Let me just go back. It's Cij is Cij plus Aik plus Bkj. So if you tell me I, j, and k, you've told me which point you are in the cube. So each cube here represents multiply Aij times Aik times Bkj and add it to Cij. So this cube is a bunch of mesh points. Each is indexed by I, j, and k. Each one represents one interloop iteration. And the faces of the cube represent the data that they need. So to do this particular multiply, A13 times B31 gets added to C11. I need to have that entry of A, that entry of B, and that entry of C. In order to multiply A21 times B13 and add it to C23, which is the cube sort of in the bottom and the back, I need that face, and that face. So what I need to do is say, if I'm only allowed to have certain numbers of entries of A, that'll limit how many squares I can have there. If I'm only allowed to have a certain number of entries of B, and I'm only allowed to have a certain number of entries of C, how many multiplies can I do? OK. So here's the simplest way to look at the picture. Here's the cube again. Here's a bunch of ijk's. These are the multiplies. So what do I need? I need some entries of A's, I need some entries of B, and I need some entries of C. So here's the simplest case. Suppose this is just a brick, and the dimensions of the brick are x by y by z. So how many entries of A do I need? Well, it's just the area of this face of the cube, z times x. How many entries of B do I need? It's just this face of the cube, of the brick. It's y times z. How many entries of C do I need? It's x times y. So it's just these areas. So the number of cubes, the number of multiplies in this black box is just obviously the area, the volume of this thing is x times y times z. That's the volume of a brick. But I can write that as the area of this, the number of entries of A, the area of this, the number of entries of B, the areas of that, the number of entries of C, and take the square root. Right? If I just multiply these areas together, I get x squared times y squared times z squared. Take the square root, and I get the volume. OK. But to get the proof to work, I have to say no matter what multiplies I do, I need this, whatever this is. It doesn't have to be a brick. Whatever multiplies I do, it's going to be bounded by something that depends on how many A's, B's, and C's I have. So here's the beautiful fact from mathematics that lets us solve the problem. So suppose now I have a general blob. I have some number of multiplies I'm doing in the inner loop, and it's some black blob in there. Which A's do I need? Well, it's the shadow. It's the projection of A. These are all the A's that I need to do all of those multiplies. This shadow, or projection, I should use the same word there, sorry, is the number of B's that I need. And if I project it up, take the shadow in the vertical direction, those are the entries of C that I need. So if I have all of those guys, all of those entries of A, B, and C, then I can do anything inside that blob. So the question is, if I'm only allowed to have a total of M entries of A, M entries of B, and M entries of C, right? Because in a segment, I have my main memory. I have M words sitting in there. And I can read another M words. That's what a segment means. So I can't have more than a total of 2M entries of A, B, and C lying around. So the theorem says that if you tell me the areas of these guys, they can't be bigger than 2M, then I can tell you the volume of this. I can tell you it's no bigger than the product of the areas and take the square root. So it's this formula, which was exact for a brick, it's an upper bound. That's all I need to know. So that this gives me what I want. The number of multiplies is going to be bounded by my memory times my memory to the 1/2 power. That's m to the 3/2. And so we're done. It's a good thing. So the volume of the cubes is bounded by m to the 3/2. That's how many floating point operations I can do. So the number of segments is the total amount of work divided by the amount of work I can do in a segment. And the number of loads and stores is n cubed divided by m to the 1/2. So that's what it comes down to. And the interesting thing is that we recently realized is this picture, which is just for matrix multiply and for things like Gaussian elimination, it kind of works for arbitrary nested loops. So as long as you can have arbitrary nested loops with arbitrary array indices in them, and we can sort of generalize this theorem about how much you have to communicate. But I won't do that today. OK.